In this video, we're going to look at conditional probability. So first off, we're going to meet Mr. and Mrs. Smith. So in this example, we will assume that the probability of a couple having a boy or a girl is equal. That is, the probability of a boy is 0.5 and the probability of a girl is 0.5. Mr. and Mrs. Smith have two children, at least one of which is a girl. So what we want to do is find out what is the probability that both of their children are girls. So take a moment and have a think about that. A possible solution that you might have thought of is that there is an equal chance of having a boy or a girl, irrespective of the information given in the question, therefore the probability is 0.5. This intuitive approach is actually incorrect. So if this was your initial answer, have another think about the sample space. So to mathematically work out the probability that both of their children are girls, considering that at least one of them is a girl, we're going to need to develop the entire sample space. So we could do this by setting up a Venn diagram. So the first child could be a boy or a girl. Then you could have a second child as a boy or a girl, second child as a boy and as a girl. So this leads to having the outcomes, and because all of these branches have the same probability of 0.5, all of these events are equally likely. So that there is our sample space. Of those, we need to reduce this because we know that we have something that's occurred. So what we know has occurred is that at least one of the kids is a girl. So that only leaves us with 1, 2, 3 outcomes that can occur. Of those outcomes, only one leads to having two girls in the family, and that's the last one, which is a girl as the first child and a girl as the second child. Therefore, the probability that both their children are girls, given that at least one of them is a girl, is 1 divided by 3, because there's one outcome that is highlighted out of 3 possible outcomes. Mr. and Mrs. Smith introduced us to conditional probability. As a mathematical statement, we're often interested in the probability of A occurring given that event B has occurred. This is conditional probability. So mathematically, we denote conditional probability as the probability of A, then we have a straight up and down line, which means given, and then we list what's given. So A given B. This is read as the probability of A occurring given that B has occurred. A formula that we can use to evaluate the probability of A given B is the probability of their intersection divided by the probability of B, which is the given event. And here we just need to know that for this formula, the probability of B cannot equal 0 because we're not allowed to divide by 0 in maths. The conditional probability formula can also be rearranged to give the multiplication rule for probability. So the multiplication rule for probability is found by multiplying both sides of this equation up here by the probability of B, and we get the probability of A given B times the probability of B is equal to the probability of A intersecting B. So next we're going to consider the sample space where the probability of A is 0.4, the probability of B is 0.75, and the probability of A intersecting B is 0.25. For part A, we want to find the probability of A occurring given B has already occurred. So we want the probability of A given B, and now as a formula we know that that is equal to the probability of A intersecting B divided by the probability of B. So the probability of A intersecting B is 0.25 divided by the probability of B, which is 0.75, and that can simplify down to 1/3. For part B, we want to find the probability of B occurring given A has already occurred. So that's still the probability of the intersection, so A intersection B, divided by the probability of, this time it's going to be A because that's the given event. So the probability of A intersecting B again is 0.25, and the probability of A is 0.4. So that can simplify down to the fraction, which is 5/8. So that there is the probability of B occurring given A has already occurred. So there's also some interesting results of conditional probability that we can have a look at now. So if the probability of A given B equals 1, then the probability of A intersecting B must equal the probability of B. So if we have a look at a Venn diagram, the probability of A intersecting B is equal to the probability of B means that the set of outcomes that are in B, that are in the event B, must sit inside the set of outcomes of event A. So we can say that B is a subset or equal to A, as all the elements in B are contained in A. If we have the probability of A given B is equal to 0, then we know that the probability of A intersecting B must equal 0. So that's the only way that our conditional probability formula can equal 0. So if that's the case, we know that the intersection of A and B must contain no elements, which means A and B are mutually exclusive events. Finally, if the probability of A given B is equal to the probability of A over the probability of B, then we know that the probability of A intersecting B is just equal to the probability of A. So in this case, we can say that A is a subset of B because all the elements in A are contained in B. Next, we're going to consider the numbers 1 to 20 inclusive, and we're going to let A be the set of all even numbers and B be the set of all multiples of 4. So that is A contains 2, 4, 6, 8, 10, 12, 14, 16, 18 and 20, and B contains 4, 8, 12, 16 and 20. If each outcome in the sample space is equally likely, find the probability of A occurring given B has occurred. So to do this, we're going to need to work out what the probability of A is, what the probability of B is, and the probability of their intersection. So the probability of event A occurring is equal to the number of elements in that set, which is 10 if you count them up, divided by the total number of elements in the sample space. So that's equal to 1/2. Then the probability of B occurring is equal to the number of elements in that set, which is 5 over the total number of elements in the sample space, which is 20. So that's 1/4. And then finally we have the probability of A intersecting B. And if we have a look at A intersecting B, we can see that B has 1, 2, 3, 4, 5 elements that all appear in list A. So the probability of A intersecting B is 5 over 20, which also equals 1/4. So we actually know, in fact, and this is what we're going to interpret in a moment, that the probability of A intersecting B is equal to the probability of B. So with this information, we're going to find the probability of A occurring given B has already occurred. So that's the probability of A occurring given B has already occurred, which is the probability of A intersecting B over the probability of B. So from the calculations on the right hand side, we know that the probability of A intersecting B is 1/4, and the probability of B is also 1/4. So we find that 1/4 divided 1/4 is equal to 1. And now we're going to get back to interpreting what we've already found before. So in the purple, we said the probability of A intersecting B was equal to the probability of B. We know that B must be a subset or equal to A, or that is all elements in B are contained in A. So if we think about that, that makes sense, because all multiples of 4 are even, so therefore all elements of B must be contained in A. So after this video, you should be able to understand that conditional probability is based off a reduced sample space, where we know that one event has already taken place. You should be able to use the rule for conditional probability to find the probability of A occurring given B has already occurred. You should also understand how the multiplication rule for probability is derived from conditional probability, which we're going to see used when we look at the law of total probability in another video. And finally, you should be able to interpret the results involving conditional probability in terms of the sets that they represent.